Hey, welcome to the video called The Atom. Today we're going to be talking about the atom, the parts of the atom, and the history of the atom. And this fits with grade 9 matter and chemical change. When you're ready, let's get started. All right, we're going to look at kind of like the brief history of the atom, the kind of the main players. I'm going to focus on four main players, but we're going to talk about five in the next little bit here. So first things first, our first guy is Mr. John Dalton in 1808. He basically said that all matter is tiny, these billiard balls. These billiard balls are all spherical and they are neutral and they are solid. What ended up happening was some guy named J.J. Thomson comes into the picture, and J.J. Thomson, what he does in 1897, he takes this device here called a cathode ray tube, and he hooks up to some electricity, so a little battery here, and he notices that in the tube, something super cool happens. What's happening here is he realizes that even though an atom is this like small sort of thing, we can actually kind of pull it apart and there's something else there. He discovered electrons. And so what he said was that in these spheres that Dalton talked about, there's actually these electrons that are sort of embedded throughout the sphere itself. Now, because he is from Europe, he called this model the plum pudding model. Because, I'm Canadian. I don't really know what plum pudding is. I did Google it, by the way. It looks delicious. But we call these raisin buns. Raisin buns, chocolate chip cookies. The idea is anything where you have something that is, uniformly blended throughout. Because the idea here is an electron here can be like kicked out, like flicked off this model. Now, in about 1908, Mr. Rutherford enters the picture and he does something called the gold foil experiment. What he does is he shoots alpha rays at this super, super thin gold foil, and he noticed something crazy. What he noticed was the alpha particles either came back at him or they went in scattered directions. So over here, like here, scattered this way, or they went directly through. And so what he realized is that, yeah, there's electrons, but there's also something called a proton. And that proton lives in that, drum roll please, the dense nucleus. So in this beautiful dense nucleus is this thing called a proton, and all of our electrons are sort of floating around outside. And that is why J.J. Thomson was able to sort of add that electrical current and send those electrons through that cathode ray tube. Now, the funny thing is when you Google model of the atom, it is this actual Rutherford's model that tends to come most often. Look at my background for this slide. But in reality, this is not the most current model. I know, shocking. You're welcome. All right, in 1922, Niels Bohr sort of put the brakes on there, and he was like, okay, yeah. You are sort of right. Yeah, there's electrons, they're outside the nucleus. However, my friends, they're in something called orbitals. Just like the planets orbit our sun in an orbit, I mean to say, in an orbit, our electrons orbit the nucleus in something called an orbital. It's kind of like the home for the electron. So what you can see here with this wonderful picture is that we actually have two orbitals. So we have this first orbital and this second orbital. And so the cool thing is the bigger the atom gets, the more orbitals that you have. And we'll talk about where those numbers come from in a bit. Now, the actual everyday model that we know is like true to this point, because it could change, you never know, is actually from 1926 from Erwin Schrödinger. And so what he did was he was like, yeah, the probably you're right, there's orbitals, but they're not quite what you picture. They're more like a cloud, kind of like this. Not these perfect little circles, but these kind of like cloud-like shapes like this. And what he says is that it's like we can't actually definitively say where an electron is found. We can't be like, yo, electron is found here today. No, my friends. It can actually be found like kind of in a whole area around the atom itself. And so we create this kind of electron cloud here. And so kind of how I like to explain this or think about it, I'm going to erase this here for you. I know I'm an excellent artist. You're welcome. I'm here all day. Is that the closer to the nucleus you are, notice how it's darker, it's denser. That means the chance of finding an electron there is really, really high. I compare this to a school, for example. If you're looking for students, in a school, the chance of finding students is most likely in the classroom. But we all know kids get up, go to the bathroom, get drinks of water, maybe they go to the office, they're going for a walk, maybe they're outside for gym. So that's all the different locations around the school. So as you get further from the school, the chance of finding a student is slimmer and slimmer and slimmer. That's why it's lighter here. The chance of finding an electron super far away from that negatively charged nucleus is small. Because remember, opposites attract. That negative electron is attracted to that positive core, that positive nucleus. And that's what's really important here, is that the further away from the nucleus you get, the less chance that you find an electron. It could still be there, but it's not as high. The pull isn't as strong. So that is our history of the atom. We're now going to look a little bit closer at an atom here, this wonderful picture. I'm hoping in your head you go, ha ha ha, why is Bohr's picture there? It's not the most current. Well, it's sort of the easiest ones to talk about because we talk about orbitals being here, right? We have one orbital, we have two orbitals, and we also have our lovely nucleus. And we talk closer about the nucleus and what that means. So our nucleus is the center of the atom. And there's a couple of key things here. There's two things that live in the nucleus. The first thing is the protons, and the protons are positively charged. The symbol that we use for protons is this wonderful P with a little kind of like uppercase, superscript plus sign. And our neutrons. Neutrons have no charge. Protons are positively charged, both letter P. Neutrons are neutral. And the symbol we use for neutrons is an N naught, or is N0 thing here. And so the cool thing is that we can actually count the protons to talk about what atom we are looking at. So when I look over here at this picture, this green one's a proton, this is a proton, here's a proton, and here's a proton. So in this picture, I have 4 protons. This actually tells me that I have a very specific atom. Now, what atom is that? So once again, I have 1 proton, 2 protons, 3 protons, 4 protons. I go to my trusty periodic table here, and I look at the numbers. So hydrogen is number 1, helium is 2, lithium is 3, and beryllium is 4. So because I have 4 protons, I know that this molecule right here is actually beryllium. Over here, let's try that again. I'm going to count my protons, my 1, 2, 3, 4, 5, 6, 7 protons. So I have 7 protons. I'm going to go to my periodic table and look for number 7. That is nitrogen. So this atom is nitrogen. I know that because it has 7 protons. My next one here, I've counted up 1, 2, 3, 4, and 5. So I have 5 protons. I go to my trusty periodic table and I see number 5 is boron. So that tells me that this atom that I'm talking about is boron. Notice that as I'm moving my way through the periodic table, my atoms are getting bigger and bigger and bigger because there's more protons that are there. Now, the electrons are found around the nucleus, like you can see here. Electrons are negatively charged. Remember, our protons are positive, making our nucleus positive. Our electrons are negative, and there's this beautiful attraction that happens to them that keeps our electrons hanging out around that nucleus. Now, because they're all negative, they spread out because opposites will actually repel each other. Now, the key thing here is that protons never ever change. If a proton changes, that means the actual atom itself changed. Just like we counted, we have like 4 for beryllium, we have 7 for nitrogen, you have 8 for oxygen. The number of protons tells you the atom. If you change the protons, you change the atom. However, something crazy is going to happen and blow your mind. Electrons and neutrons can change. If I change my electrons, that means I am now making an ion. I know, shocking. You're welcome. So you're probably wondering, what's an ion, Mrs. Carter? Oh, I got your back. Don't worry. So an ion is when the number of protons and electrons are not the same. That means they're not equal. We have 2 sort of situations that can happen here. You have a positive ion, which means that you have lost electrons. It's a positive ion because, once again, the nucleus is positive. So if you lose negatives, that means you're overall positive. The elements on our periodic table that we have positive ions over here is I'm going to take my beautiful staircase that is right here like this. Remember, on this side are my metals and this side are my nonmetals. The elements that make your positive ions are actually your metals. So this side over here makes your positive ions. These guys are like, yo, I have an electron. Who wants to take it? Guess who takes it? Your metals do, because your metals like to gain electrons. They really want those electrons. So your non-metals are like, metals like, here, someone take my electrons. And non-metals like, I got your back. I'll take your electrons. So metals tend to be positive, and we call them cations, whereas non-metals tend to be negative, and we call them anions. Once again, lose electrons, you become more positively charged. Gain electrons, you become more negatively charged. So let's practice that. So first things first, that 15 there, that is your atomic number. It tells you, bam, how many protons that you have. Remember, this number changes, the actual atom itself changes. Now, this number over here is actually called your ion charge. Oh, there it is, ion charge. My ion charge is negative, so it's telling me that my phosphorus, if it becomes an ion, has gained 3 electrons. That's a key thing here. Down here, this is my atomic mass. This tells me how many protons and how many neutrons I have. So let's practice that for a second. Oh, I'm going to go back here for a second. So if I was to figure out in my atom, okay, so remember in an atom, your protons are equal to your neutrons. Sorry, electrons. I'm not going to restart this video because I've made this like 7 times already. So when I look here, my number of protons is found up here, which is 15. So if it's an atom, that means I have 15 protons and I'm going to have 15 electrons. If, for example, it's an ion, because my protons do not equal my electrons, right? My protons do not equal my electrons. What ends up happening is if I start with 15 electrons, right? Because in an atom they're equal, it's telling me that I'm gaining 3, so I need to add 3 electrons to that. So that means that overall, I'm going to have 18 electrons in my ion. Okay, let's practice that. So once again, here's my element, phosphorus, right? My number of protons comes from my atomic number, which is 15. It tells me that it doesn't say ion, so I have to assume it's an atom. If it's an ion, it will tell me that it's an ion. So it's an atom, so my protons and my electrons are equal, so therefore it is also 15. To find my number of neutrons, because neutrons can change, I need to take my atomic mass and subtract it from my protons. Because remember, the atomic mass is both your protons and your neutrons. So I take my 31 and I subtract it from 15, which means I have 16 neutrons. I'll try that again. Beryllium ion. Ooh, that got exciting. So we have an ion here. So that tells me that my protons and my electrons are not equal. Number of protons always comes from up here in this corner, the atomic number, which is 4. My number of electrons is going to be different because I have, because I have different numbers. So I start with 4 electrons, right? Because it's an atom, it's an ion. So I look here. This tells me that it loses electrons. Okay, as it loses, it means I lose 2 electrons. So I'm going to take away 2 electrons. So that means overall, I'm going to have 2 electrons. My number of neutrons comes from taking my atomic mass, my number 9, and we're going to subtract it from my number of protons, which is 4, which means I have 5 neutrons. Bromine. So bromine itself doesn't tell me if it's an ion or anything like that. So bromine, I'm going to look at my atomic number up here, which is 35. Because it doesn't say ion there. I know it's an atom. Protons, electrons are equal in an atom, so therefore it's 35. So once again, this is an atom. And I know that because it doesn't tell me anything different. To find my neutrons, I'm going to take this nice number here because it tells me that's the isotope that it is. If I didn't tell you that, you would take this number down here and you would round it to an 80. But I've told you to use 79. So take 79 minus 35, which gives me 44. What about phosphorus ion? So once again, my atomic number up here gives me the number of protons. I know that it's an ion because it tells me that. So I'm going to start with my 15 electrons found in the atom, and I look over here at my ion charge. It's negative, so that means it gained electrons. So I'm going to add 3 electrons to it, which means that I'm going to have 18 electrons in my ion. My number of neutrons comes from taking this number right here, or this number rounded. I take my 31 and I minus it from 15, which gives me 16 neutrons. Magnesium ion. So once again, atomic number tells me 12. It's an ion, so my protons and electrons, they are not equal. So I need to start with my 12 electrons and look at my ion charge. The ion charge is positive, so that means it has lost electrons. How many? 2, because it's 2 positive. So I'm going to minus 2 from it, which then tells me I have 10 electrons. Neutrons, I'm going to take this number here because it tells me it's 24. We always use a whole number. I'm going to take my 24, subtract it from my 12 protons, which gives me 12 neutrons. Beryllium, it doesn't say ion, so that means that it is going to be an atom. An atom means that my protons and my electrons are the same. So it's 4 and 4. Once again, I take my atomic mass, which is 9, subtract it from my atomic number, which is 4, and I get 5 neutrons. Whew, how about magnesium? Number of protons comes from my atomic number, which is 12. My number of electrons, it doesn't tell me ion, so therefore I know that it is an atom. In an atom, my protons equal my electrons, which means I have 12 electrons. My neutrons comes from this beautiful rounded number, 24 minus 12. The 12, once again, comes from here. Okay, and 24 minus 12 is 12. All right, my friends, let's recap this. So, history of the atom. First model, John Dalton, billiard ball. Bam, discover electrons. J.J. Thomson, got electrons, raisin bun model. Then we're like, yo, electrons are not inside the nucleus. It's actually spread throughout, which is model here, which is Rutherford's model, which are kind of whizzing around, kind of willy-nilly out in the space around the nucleus. And then we move into our Bohr model, which is like, yeah, there's the nucleus, but they're actually something called orbitals. Finally, parts of an atom, the center is the nucleus. Protons are positive, neutrons are neutral, electrons are negative. An atom, the protons and electrons are the same. An ion, the protons and electrons are not the same. Thanks for watching.